Guess the wrong name for you, like I've been doing. For some reason, just some other name reminds me of you. That other person's on mine. I know that's not you. All right. Let's see. Are you wearing WVSU gear? Morning. Sure. Yeah, got it. WVSU gear. Extra points for you. So we are recording, by the way. If you guys have any questions, feel free to ask. I just like to make sure we're recording that way. If I watch the video afterwards, so it gets the benefit. Me answering any questions you might have. Or anybody who comes in at 8. They would naturally miss your questions, but then, like you said, you can watch the video. Well, we've got a minute left, so I might as well do attendance. I think I've got everybody who is here, so I'm just going to call out the names of people I think are not here. So, obviously, I call your name. Correct me. Gazelle, Valdez, Page, Aya, Stanley, Cunningham, Newton, Mousa, Smith, and Carr. I have on mine Black, Sims, Fisher, Davis. Double check that. Yep, that is correct. So everything seems to be in order as far as attendance is concerned. I'll wait till actual 8 o'clock before we get started. Which should be here in a few seconds. Yep, 8 o'clock. We will get started. Let's start with some announcements / reminders. The first announcement / reminder is make sure you're reading Google Classroom. I keep posting things, and they're very important. And I have reason to believe only a few of you are reading it. Once you read it, you'll understand why I have reason to believe only a few of you are reading them. But please read them. I try not to post them often, which is why they're long, because I try to condense a lot of information in one post. I don't want to bombard you. So I even have it broken down, but it's hard to see right here. Right here it says new information. So make sure you read the new information. And then the old information is there if you just need to like refer back to something. Like you're like, I know he said that there's a video that shows how to do independent work. So you can just refer back to that. Does that make sense? So the old information is there. If you just want to refer back to stuff, I'm just repeating myself for that. The new information, at least read that when I post it. You'll trust me, it'll help you. And like I said, I have reason to believe a lot of you are not doing that. Also to remind you, speaking of reason to believe things, you need to read the syllabus. There will be at least a few questions about the syllabus on the exam, so make sure you read the syllabus. Again, I have reason to believe if you haven't done that, I have my ways of knowing, and once you figure it out, you'll see what I'm talking about. Anyway, any questions about Google Classroom? All right. Other announcements, lab, to remind you, if you were physically in lab last week, you have nothing to do today. You don't have to come to lab. If for some reason you really enjoyed that lab, or you just need some extra help with it, everybody's welcome to come to lab today. But if you were here last week, you do not have to come to lab. For those of you who do need to come to lab, be here at noon. Don't be late. You'll lose points if you're late. It's very important that you're on time, because usually it's a team effort. Usually we're all depending on each other to get labs done. So if you come in late for lab, which is a little bit less important. If you come in late for lab, then I've got to repeat myself, or you're going to be missing important information, and then you're just going to screw everybody else up, right? So that's not good. So yeah, that's the deal with lab today. And again, if you're coming, as always, bring a computer if you have one. Otherwise, some scrap paper would be great. Because you're going to do the information. You're going to write all your information down here, but then it needs to be posted online. So to remind you, the lab for today or last week, depending on when you haven't had it, will be due Friday. So the cutoff date is Friday to have it turned in. Good? Of course, if you don't know how to turn it in, or you think you remember, but you're not sure because I've been giving you so much information, just come to me. If you need my help, come to me and I'll show you how to do it. So next week's lab, that's the chemistry lab. To remind you, it's already posted, and you need to do the pre-lab by Sunday. Of course, the due date's there, so if you forget what I told you, that's okay. You can just look right here, upcoming due dates. This lab that we just did, due Friday at 11:59 p.m. The chemistry lab, the pre-lab, is due Sunday at 11:59 p.m. Any questions about lab? Okay. To remind you, it's WVSU Wednesday, so anybody who's wearing the WVSU gear any Wednesday is going to get a little bit of extra credit. So I think you guys already know that. Matthew, I need to adjust yours. Make sure you email me today. Both of you email me to let me know that you came in late.
Gotcha.
And then, of course, we'll do the picture if we have time and anybody wants to do it. Same thing for Fridays. If you wear red on Fridays, you get a little bit extra credit. And if you participate in a picture, you get a little bit more extra credit. Any questions about that? All right, the last question, I have a question for you guys, is when's the first football game? Does anybody know? No, I don't need it. I feel bad, but my life's been really hectic. Anyway, if anybody goes to that same situation like I've been posting on Facebook, all these different opportunities, if you go to a football game, and you prove it with a picture of yourself there, you get a little bit of extra credit. Obviously, if you're wearing WVSU gear while you're there, a little bit more extra credit. And then probably like if you share it social media, a little bit more extra credit. Just trying to promote the university and giving you guys extra credit for doing so. So any questions about any of the announcements or reminders, or any other announcements or reminders that you might have questions about before we jump back into chapter 2? All right, that's it. So for those of you online, as always, even though I called your name, the four of you, you still need to send me an email when we're done and give me the keywords. The first keyword for those of you online is banana, like the yellow thing that you eat. Let's jump into this. 1 second. There we go. Oh, why are they doing that? Sorry, let me fight with technology here for a second.
I wasn't here when you were first talking about the lab. If we missed last week, we come today, right?
Exactly. Make sure, the other thing I was saying is make sure you're on time. It's so important to be on time for lab, more so than the lectures. All right. Yeah. Sorry, I'm still fighting on this screen. Screen 2. Share. Then. Sorry, if you're online, I have no way of verifying this. I don't think. Actually, let me try one more thing. I apologize, guys. Yeah. Should be good now. Okay. Anyway, let's jump back into it. Let's remind you of what we're talking about. We're still in the first main bullet point, the first of one of two main bullet points for chemistry. We're talking about some basic information. First, we talked about what matter is, anything that occupies space and has mass. And we talked about what mass is, and it's basically the amount of stuff, right? The measurement of how much stuff, whether that be how much something weighs or how many fluid ounces it is, before, how many milliliters it is, something like that. We talked about compounds and elements, so an element is like carbon, for example. Carbon's an element. It is the only element where the atom has 6 protons, for example, because its number is 6. And remember, an element is defined by its number of protons. So anyway, we talked about elements, gave you some examples. I told you about the big 4 for your body that you need to know. So you are mostly made up of carbon, oxygen, hydrogen, and nitrogen. You need to know that. I also said you probably don't even need to study that because starting next chapter, you're going to get so sick of those. That's all we're going to talk about for the most part is carbon, hydrogen, oxygen, nitrogen. So you shouldn't have any problems remembering that. Then we got into compounds. And we said basically when 2 or more atoms come together in a fixed ratio, that's a compound. Some of the examples we used, even though you don't need to know them for the exam because they're just examples, water, right? Water is always H2O. If there's any other version of that, it is not considered water. It's got some other name. Another compound would be salt, table salt, right? Sodium chloride, that's a compound. Then we talked about atoms. You need to know that the insides are the protons and the neutrons all stuck together. You need to know that the outsides, you have electrons orbiting them. You need to know electrons are negative, protons are positive, neutrons are neutral. You need to know mostly it's the electrons that are involved in chemical reactions. And that's mostly it. And we talked about other stuff. I'm just trying to catch you up briefly. Then we got into this bullet point here, this main bullet point, which we're talking about the different types of bonding and the different types of molecules. First one we talked about was ionic bonding. And again, I gave you the example of salt, table salt, sodium chloride. An ionic bond is when you have 2 ions together. And to remind you what an ion is, when something gives up an electron or takes an electron, it has a charge, right? Because it's either extra negative or extra positive. So those are ions, and because they have because they're charged and they have opposite charges, they're attracted to each other, like 2 ends of a magnet. And that is an ionic bond, when you have 2 ions together. Pretty simple, right? All right, that brings us to the new information, covalent bonds. First of all, what does that prefix co mean? Like, for example, let's talk about something outside of science. If I said my daughter is cohabitating with one of her best friends, what does that mean? Living with, right? So it's a with kind of thing. A co-conspirator, right? If you're talking about maybe political stuff or criminal stuff, that's somebody, at least 2 people who are like, doing bad things together, for example. So how about this word? I know I've mentioned it a little bit on Monday, but I don't know if I said it enough. Valent or valence. Does anybody know what the valence ring is?
Oh, it's the outer rings.
Yeah, it's the outermost ring. And we did talk a little bit about this, where I used carbon as an example. I said, and you will get a question like this, definitely in lab, maybe in the exam. I might just give you information like carbon's number is 6. Its atomic number is 6, right? So carbon, its number is 6. From that information, you know that carbon has 6 what? What does that number mean? 6 what? Is it 6 years old? Does it weigh 6 pounds? Is it married to 6 other elements? What does 6 mean? What does that mean it has? And you do need to know this. Good, perfect. It has 6 protons. So I haven't said anything about this thing being charged, so it's neutral then, right? So if it has 6 protons, then how many electrons must it have? Perfect, 6, right? Because if it had 1 more than that, it would be negative. If it had 1 less than that, it would be positive. So we know that carbon's number is 6, therefore it has 6 protons, 6 electrons. Then I said we could draw it. We don't even need to draw all 6 protons, and I'm going to completely forget about neutrons for this conversation. So right there in the nucleus, we have 6 protons. And then we have a ring. And again, I understand if you don't remember this because I just told you Monday, but eventually you will need to remember this. How many electrons are on that first ring? Good. So here we go. Got 2 taken care of. And we have 6 total, so 6 minus 2 is 4. So I just draw the other 4. 1, 2, 3, 4. There we go. So that outermost ring, that thing is called the valence ring, right? That's what we're going to call it. And just as a quick review, even though it technically, yeah. How many is this supposed to have total? 8, good. And like I said, it has 4 here, right? So therefore, we know it needs 4 more, correct? That's where this comes in, covalent bonds. And this is just an example. A lot of other elements do covalent bonds other than carbon. But yeah, we need 4 more electrons for that thing to have a full outer ring. Therefore, we know, this is the new information here, carbon can bond 4 times. can do 4 bonds. So that means it could do like, it could bond single bonds to 4 different atoms, or maybe double bond to 2 different atoms. We'll talk about that later. But for now, the point here is that outermost ring is called the valence ring. So therefore, hopefully, the name explains itself now. Covalent bonds are the ones where the atoms are sharing electrons from their outermost ring. Covalent bonds. Atoms share 1 or more pairs of electrons. And really, I keep it pretty simple in this class. So yeah, technically it is a pair of electrons, but I'm not even worried about that. At this point, just know if it's a covalent bond, they're just sharing electrons. And if it helps you remember the name covalent, then remember that they're sharing it from the outermost ring. But that's only if it's helping you. As far as I'm concerned, what you really need to know, if you're taking shorthand, you could write covalent bonds equals sharing electrons. Unlike the ionic bond, which is what we talked about on Monday, right? Ionic bond, they're not sharing them, like, all right, this one's yours, this one's also mine, we're gonna share them. No, in ionic bonds, one of them gives up an electron. The other one takes it. Here's another thing you definitely need to know. This will be very important for chapters to come. So this isn't just important for the exam, this is important for understanding other concepts that are coming later in the semester. Covalent bonds are the strongest of the 3 bonds that we talk about. Strongest bond. Another thing that I find a little bit less important, so, as far as a little star next to it, I can't do a star like that, it's okay. Anyway, put a little star next to that because I find this less important as far as the exam is concerned. The only reason you need to know what a molecule is that way you understand what I mean when I use the word. But technically, when it's 2 things coming together and it's a covalent bond, it's a molecule. Which might sound confusing, but think about what you learned on Monday. If 2 things come together in a fixed ratio, you already know that's a compound, right? So you have this big category compound. And under that are subcategories. Like an ionic compound, is a type of compound. And now you know, too, that a molecule is a type of compound. Again, for the exam, that's not that important. I'm not trying to confuse you. I just need you to know what that word means when I use it. Like I already said in this picture over here, the reason we have these bonds is because these atoms are trying to fill their outer electron shell. That's what it's all about, especially with covalent bonds. Well, all the bonds, both ionic and covalent bonds. They're trying to get a full outer ring. So in this case, because carbon has 4, that means it needs 4 more. That means it's going to bond 4 times. Oxygen, for example, is a different number. Its number is 8. So if I were to draw it, because we know it has 8 protons, it must also have 8 electrons, because it hasn't said anything about it being charged. So we have 1, 2, 3, 4, 5, 6, 7, 8. So for example, this thing has a total of 1, 2, 3, 4, 5, 6 on the outermost, and it needs a total of 8, which means oxygen can bond twice. Make sense? All right. Now, when you're studying, this is one of those things where it's more important that you can work something like that out. So I don't need you to memorize that carbon can bond 4 times or that oxygen can bond twice. I need you to be able to figure that out. I need you to be able to, when I give you anything on the periodic table and give you the number, you should be able to figure out, all right, it's that many protons, it's that many electrons, 2 on the outermost, 2 on the inner ring, 8 on everything else, and then you can figure out how many times it bonds. Anyway, any questions about what's on the slide, this particular slide? All right, the next word for attendance, inspired by this little stupid thing, this is going to be Hawaiian shirt, or just shirt. The next word for attendance is shirt. If you're online, that is the second word for attendance, shirt. The next slide I'm going to go through really quickly because I've already drawn it for you. Now you're going to see the same thing again. There's carbon with its 6 protons, therefore, or its atomic number 6, therefore we know it has 6 protons. Because I haven't said anything about it being charged, we know it must have 6 electrons. Therefore, again, if you draw it out, you have 2 on the inner shell, and then 6 minus 2 is 4. Okay, so on the outer shell, you draw 4 more. That means we need 4 more for it to be full, therefore it can bond 4 times. And again, I know I went through that quickly, but that's because I've already drawn it on the board. So if anything, this is for the people online who might have a problem seeing the board, you shouldn't have any problem seeing the slide. So any questions? All right, so again, remember, please, you don't need to memorize the fact that carbon can bond 4 times. You just need to be able to figure this out. If I give you the name of an element and its atomic number, you should be able to figure the rest of that out. And of course, this isn't a chemistry class, so if you see a question like that on the exam, there may be 1 or 2 at the most, out of 50-ish. So if you're having problems with that, don't feel stressed, just do your best. Another thing your book shows you is there's different ways of drawing molecules. You don't need to memorize any of this. I'm not going to give you a bunch of molecules and say, all right, which one's the electron configuration? Which one's the structural formula? Which one's the space-filling model? Which one's the ball and stick model? You don't need to memorize any of that. I will tell you that one of the ones we're going to work with a lot is this one, the structural formula. That's what you're going to be doing in lab next week. But you don't need to memorize any of that. This is just to show you, I don't want you to get confused. Like, if you're reading the book and you keep seeing something that looks like this, what I'm talking about formaldehyde, and then you come into class and I'm talking about formaldehyde and I draw something like this, I don't want you to just think, what? That's not right. The book says something different. I just want you to realize there's different ways of representing molecules. There's actually a whole different way that's not shown on here that we use in organic chemistry, but that's a different story. So anyway, any questions about this slide? Okay, so again, you don't need to know those things. This is just to show you that there's different ways. And another thing you don't need to know is the structure of formaldehyde. I'm certainly not going to show you that. You're like, all right, which molecule is that? You don't need to know. All right, if you were to download this PowerPoint, you can watch this video. It's a little animation that shows a covalent bond forming. So there's that if you want it. I've also shared other videos on Google Classroom that are better than this one, and that you can get independent points for watching as long as you answer the questions while you watch them. So that is all we have to say about covalent bonds. Are there any questions about ionic bonds or covalent bonds? All right. Next one we're going to talk about is a little bit more complicated, and it's hydrogen bonds. Before I can really even get into what a hydrogen bond is, you need a little bit of background information. So we use water as an example. That's the biggest example for this. As you probably already know, the chemical formula for water is H2O, meaning it's 1 oxygen combined with 2 hydrogens. Specifically, I'll just draw it. Oh, no, right there. Specifically, that oxygen has 1 hydrogen each attached to it, as opposed to it being like hydrogen attached to a hydrogen attached to an oxygen. That won't work, and you'll learn why in lab. Anyway, water, again, is an oxygen combined with 2 hydrogens in covalent bonds. But here's the thing where it gets a little bit more complicated. But you know, because it's covalent, that they're sharing electrons, right? But they don't share them equally. For example, let me try to explain it. If you were to look up there, actually it's right here, I just told you. What is what is oxygen's atomic number? Not that you have to memorize this, but I just told you, and it's right there, and it's on the periodic table. So someone tell me oxygen's atomic number. Good, perfect. Its number is 8, which means what? It has 8 what? Good. That is important. Not the fact that oxygen has 8, but remember, this part you do need to know. When you know the atomic number, you need to know that means that's how many protons it has. Oxygen has 8 protons. Anybody want to look it up behind you and tell me hydrogen's atomic number? Or if you just know, you can tell me. And I'll give you a hint. It's at the top left of the periodic table. 1. Hydrogen has 1 proton. So its atomic number is 1, therefore it has 1 proton. All right. What charge are protons? Is it neutral? Is it positive? Is it negative? What's the charge for a proton? Positive, right? So hydrogen has this 1 positive thing. Oxygen has 8 of these positive things. Now, what is attracted to positive things? What's attracted to these protons? Electrons, right? Because electrons are neutral. So if you're an electron and you really like positive things, you have to go between these two. Where are you going to go more towards? The thing that has 8 protons or the thing that has 1 proton? 8, right? Because that's a lot of positive. So if you're attracted to positive, you're going to be hanging out a lot more towards the oxygen end. Does that make sense? Sort of like if your parents were divorced when you were a kid, and technically they have shared custody, but one parent's got all the stuff you like, all the video games, lets you stay up late, lets you eat what you want, all the things you want. The other parent, not so much, right? So technically you have shared custody, they have shared custody. If you get to choose, you're choosing more towards hanging out with the other parent. Right? Same thing here. So water, again, and not just water is just the one we're using as an example. The electrons are not always shared equally, and when that happens, and you need to know this, at least for the study guide, perhaps for the exam, when this happens, when there's a molecule where the electrons are not shared equally, that's called a polar molecule. A polar molecule is when there is an unequal or uneven distribution of charge. And of course, as we know, the charge is coming from those electrons, right? So in this case, I'll just show you another picture here in a second. I still see you still taking notes. So yeah, definitely know that you need to know for sure that water is a polar molecule, and you need to know for sure why. That's because, again, it's an unequal distribution of charge, because the electron's more attracted to the negative end, which is the oxygen, or I'm messing that up. The electrons are more attracted to the protons, the oxygen, which makes it more negative, because that's where the electrons are. Any questions about this slide before I show you a picture of what I'm talking about? You go too fast. All right. So again, like I said, these electrons are hanging out more towards the oxygen than they are the positive. Which could mean the oxygen more than the hydrogens. So because of that, this end of the molecule is slightly negative, while the oxygen ends are slightly positive. Because again, the electrons are now hanging out closer towards the oxygen than they are the hydrogen. And this results in a weak attraction between neighboring water molecules. And I'll show you a picture of that on the next slide. And that's what a hydrogen bond is. So again, as a reminder, ionic bonds are when atoms give up electrons or take them, right? And they become charged, they become ions. And that's why they're attracted to each other, because they have completely opposite charges. Covalent bonds are when they share electrons. Hydrogen bonds are when there's a slight difference in the charges of the atoms. And it looks like this, at least for water. So this is what water looks like if you were to look at the molecules. Positive hydrogen end of this water molecule is attracted to the negative, slightly negative end of that water molecule. Same here. That slightly positive hydrogen is attracted to this slightly negative oxygen. This slightly positive hydrogen is attracted to that slightly negative oxygen. See how it works? All right, so there's 2 questions on your study guide, and they will probably be on your exam, and people always miss them. I don't mean for them to be tricky, you just need to pay attention. One of the questions says, what holds together a water molecule? And if there was a picture, it would be this, right? What's holding together that? What kind of bond is holding together that one molecule? And what is the answer? I know I just gave it to you, so feel bad if you don't remember, or if you're afraid to say. All right, so the thing that's holding this one water molecule together is covalent bonds. That hydrogen is covalently bonded to that oxygen. That hydrogen is covalently bonded to that oxygen. So there will be a question that says, what holds together a single water molecule? Then there'll be a separate question that says, what holds together adjacent water molecules? Right? So not this one water molecule, not this one water molecule, but what's holding all these together? And the answer is hydrogen bonds. Any questions about that? All right, another thing I didn't see in writing on my slide that I need to fix, because you definitely need to know this too. I told you that covalent bonds are the strongest of the bonds. Hydrogen bonds are the weakest. And again, that's not just important for the exam, but to understand some concepts that are coming later in the semester, and often in the semester, you need to understand covalent bonds are the strongest and hydrogen are the weakest. So this really is important. To understand the stuff that you're going to learn in Chapter 3, Chapter 5, you need to understand these concepts you're learning in Chapter 2. To understand the things that are coming in Chapters 6, 7, at the very least, You need to understand the things that are in this chapter and in chapter 3 and in chapter 5, right? So this is all cumulative in a way. Not as much as like algebra, but it is cumulative. Anyway, any questions about hydrogen bonds or any of the other two bonds? All right. Let's talk about chemical reactions. Now that we're done talking about the 3 different types of bonds. Your book points out that cells are constantly rearranging molecules. And what I mean by that is they are breaking bonds and forming new ones, right? So that's, again, other than all the cumulative stuff I just told you about. Another reason that chemistry is important for biology is because cells are constantly doing this. There's constantly chemical reactions happening in your body. And we'll scratch the surface on this and you'll realize that it's those chemical reactions that are keeping us alive. Without those chemical reactions, we'd be dead. And I don't mean like eventually dead, I mean immediately dead. So, when we have these changes in the chemical composition of matter, we call those chemical reactions. What do I mean by changes in the chemical composition? What I mean is this, for example, right? Here we have hydrogen peroxide on one side, 2 of them, and each hydrogen peroxide consists of 2 oxygens and 2 hydrogens, right? So then it goes through a chemical reaction, and then you have 2 molecules of water and 1 molecule of oxygen. Point being here, that's what makes it the changes in the chemical composition, right? We still have the same, look, 1, 2, 3, 4 oxygens on the left side, 1, 2, 3, 4 oxygens on the right side. 1, 2, 3, 4 hydrogens on the left side. 1, 2, 3, 4 hydrogens on the right side. So the matter itself didn't change. We still have the same number of atoms, we still have the same types of atoms, but the way they're put together, that's what changed. So that's what we mean by the change in chemical composition. I'm almost definitely not going to ask you the definition of chemical reaction in the exam, but there you go. Now you know what it is. What you do need to know, and again, I'm not sure if I'm going to talk about it or put it on the exam, so I'll put a question mark here. But you definitely need to know it because I'm going to use these words a lot, at least through the first half of the semester. The reactants are what you start with and the products are what you end with. And as far as we're concerned in this class, the reactants are always going to be on the left and the products are always going to be on the right. Another way of putting it too is the arrow is always going to point from the reactants to the products. That is important for you to know. Again, less so because I'm going to ask questions about it on the exam, but more so because you need to figure stuff out and understand stuff information that I give you. So you need to understand those basic things. All right, and like I've already hinted at, because I said this is a change in the chemical composition of matter, what's happening in the chemical reaction is we're just rearranging the matter, right? We're not creating new atoms. We're not destroying old atoms. We're just rearranging them. And of course, there are some ways where you can destroy atoms, right? Nuclear reactions. You take uranium and you split it, so to speak. And then you're left with different elements, right? But that's a different story. That's not a chemical reaction, that's a nuclear reaction. So again, we're only talking about chemical reactions. And this is also a very important bullet point. Matter cannot be created or destroyed. Therefore, obviously, chemical reactions do not create or destroy matter. Because again, there's no extra oxygens on one side or the other. There's no fewer oxygens from one side to the other. Because nothing was created or destroyed as far as the atoms are concerned. It was rearranged. Any questions about this slide? Okay, the next word for attendance if you're online. Let's go with, why not, reactions. So that's your next word right there. You're online. All right, no questions, then we'll move on to the last main bullet point of this chapter. We're making great time, which I hope isn't a bad thing. I hope I'm not going too fast for you. Please tell me if I am. The last thing we're going to talk about this chapter is this relationship between water and life. Why is water so important? And then also, I'll take a little bit of time to slow down here, plan ahead. If we finish chapter 2 today, and we will start chapter 3 on Friday. Which might be good. Anyway, yeah. So let's get into it. Water and life. Not that you need to know the information on this next slide, but as far as we know, life began in water, at least life on Earth, right? It began in the oceans, in water, and it evolved there for 3 billion years before finally it came to land. It's really interesting to look at that stuff up too. If you want to look at, compare some of the life forms that have lived in water a long time ago versus life forms that are on land right now, you can see like what came before what. I'll try to find some good examples for you, but it's something worth looking into for individual work if you want. Like obviously sharks predate flowering plants, for example. I don't know, I find that kind of stuff interesting, but I'm a biologist. Anyway, yeah, life began in water. It's been there for a long time. It came on the land eventually. Life is obviously still tied to water, so obviously there's still life in water, but also the life that's on land is still dependent on water. Here's a number you do need to know. I'm not big on numbers in this class, but this one you need to know for the exam. Your cells, or the average human cell, I should tell you, is about 70 to 95% water. That's a lot. Think about that. Like if you were to look at a cell, a large majority of it, especially if it's on this larger end, 95%, it's almost all water. So obviously that should tell you water is important for life, right? Because mostly you are made of water. And as we're going to talk about later, so there's no need to write this bullet point down, but this abundance of water on Earth is a major reason that it's habitable. Not just because, we need water to drink, or because we're made mostly of water, but as you're going to learn later in this portion of the chapter, it's also because the reason life or the Earth isn't too hot or too cold is because of water. So this is just the introduction to this main section called Water and Life. Are there any questions so far? All right, it's only the thing circled right there that you need to know for the exam. That's the only thing, as far as the exam is concerned, that's important on this slide. So we just learned about water. We learned about hydrogen bonds. And it's worth noting that it is that polarity and those hydrogen bonds that explain all this stuff that I'm about to tell you about why water is important. It's almost always boils down to the fact that water molecules are polar, and because of that, they have hydrogen bonds. You don't need to write this down because we're going to talk about each of them separately. But the 4 things we're about to talk about is the cohesive nature of water, which is basically how water sticks together. But polar bonds, right? Its ability to moderate temperature, which is also, not polar bonds, polarity, hydrogen bonds, okay. Also its ability to moderate temperature, which you'll see is also related to the fact that there's hydrogen bonds keeping them together. The biological significance of ice floating, which is loosely tied to the fact that there's hydrogen bonds there. And the versatility of water as a solvent. So again, that will be tied into the fact that there's hydrogen bonds. So any questions about this introduction of the slide? Okay. Oops. Yeah, first thing we're going to talk about is the cohesion of water. Again, like I just said, when I say cohesion of water, what I mean is water molecules stick together. That's what cohesion means. Like if you're in the military or you play some sports and they say, oh yeah, that group of people, they're very cohesive. Meaning that group of the same people, whether it be the same unit or the same team, they stick together, they're cohesive. Not that you need to know this, but if I were to stick something to this wall, like a sticky note, that wouldn't be cohesion, that'd be adhesion. Because it's still stickiness, but instead of 2 of the same things sticking together, it's different things. But you don't need to know that. Just throwing it out there. So again, that is the definition of cohesion, as far as we're concerned in this semester. Molecules of the same kind sticking together. That is cohesion. And the important part, not necessarily for the exam, just for understanding all this information I'm about to give you, the cohesion is stronger for water than most other liquids because of those hydrogen bonds. There's a lot of things that have hydrogen bonds, but they don't quite have the same hydrogen bonds as water. For example, rubbing alcohol. You ever put rubbing alcohol on you? How does it feel? Not if it's a wound that burns, like it stings, but what happens if you were just like put rubbing alcohol on your skin without a wound? How would that feel to you? You've never done it. It's usually cold. It feels cool, right? That's because it's evaporating. Because there's fewer hydrogen bonds in alcohol than there is water, so it just quickly evaporates. And when it evaporates, it makes you feel cool. We'll talk about that later. Anyway, getting back to the cohesion of water. Your book, I think, if I remember correctly, only uses this example. Because you can look into other examples for independent work. Why is the cohesion of water important? Other than this one example I'm about to give you. But trees depend on the cohesion of water to transport water from the roots to the leaves. Have you ever thought about that? Have you ever seen like those 300-foot sequoias and wondered how in the world do you get water from the root to that very tip-top leaf? It's not like trees have pumps. They don't have water pumps, right? It's working against gravity, so it's not like water's flowing down gravity when it goes from the roots to the leaves. It's not like the leaves are absorbing the water that's in the atmosphere or the rain that hits them, right? It's all coming from the roots. So let's talk about how. It's almost like a chain reaction. So way at the tip top, or wherever the leaf may be, water does evaporate from the leaves. Some of it's used in chemical reactions, some of it just escapes. And when it escapes, it just leaves. Right? I know it's a little bit hard to see, but like, let's say that water molecule just pops out, right? Leaves through one of these tubes, it's gone. But because it was attached to that one kind of moves up and takes its place. And of course, that one was attached to that one, so it moves up and takes its place, so on and so forth. It's basically a long chain of water molecules. So if you pick up one and get rid of it at the very tip top of the tree, then they're all going to come from the bottom. Does that make sense? That's how we describe it in this class. It's a little bit more complicated than that, maybe, if you were to really look into it. But as far as we're concerned, that's good enough. If you're online, you may not have seen what I was pointing at. So what I mean is like this water molecule here, if we were to just up and leave, from evaporation, and the rest of those will follow behind. So, any questions about how water gets from the roots to the leaves? All right. Actually, I forgot. There's one more example that your book gives about why cohesion of water is important for biology, and it's surface tension. Of course, this is a lot less important, I think, than trees getting the water, but anyway, surface tension is the measure of difficulty in stretching and / breaking the surface of a liquid. So again, it's it's the hydrogen bonds that give water its high surface tension. And it makes it behave as though it was coated with an invisible film. So here we have a picture of a spider standing on top of the water. It's not necessarily floating, it's literally on top of the water because it's not broken surface tension. Anyway, any questions about what surface tension is? As far as the grand scheme of this semester, it's a little bit less important of some of this other information, so I'm not going to talk about it too much. Here's a picture of surface tension from maybe the 2016 Olympics. I don't remember which one it was, but I know it's a little bit hard to see, but the water level's here, the water line. So this person's a little bit above the water line, but still underwater because that person has not broken the surface tension yet. Just an example. And then another picture. I like this one because it's our mascot. So there's a picture of a wasp, a yellow jacket, on the water, right? And then also a neat little picture of its shadow. But anyway, any questions about the cohesion of water? All right, the next thing we're going to talk about is how water moderates temperature. So there's a strong resistance to temperature change with water than there are most other substances. Meaning, when you try to heat up water or cool it down, it actually takes more energy to do that. How many of you either do this or have seen it done where after somebody's cooking, they'll put like a tea kettle of water on that eye. Right? They're done with that eye, but it's still hot, so they put water on. You guys ever seen that or do it? Anyway, that's the reason why. Because when you put it on there, it's going to absorb that heat, that leftover heat on the eye. Meanwhile, if you just kept it out, first of all, obviously you could accidentally burn yourself. But this is putting that heat off into your kitchen. Anyway, let's talk about why that happens. When water is heated, this heat energy first disrupts the hydrogen bonds. Actually, let me back up. Before I even tell you about that, let's talk about what heat is. A at the molecular level, if I say the air temperature is getting hotter in here, what do I mean? What's happening to the air molecules if it were to get hotter in this room? What are the air molecules doing? Are they moving faster or are they moving slower? Faster, yeah. And a good way to remember that is, if you rub your hands together slowly, it gets a little bit warm. The faster you do it, the warmer it gets, right? Because temperature really is, or heat really is just a movement of molecules. All right, so remember that. When we say something's getting hotter, what we're meaning, whether it be water or air or whatever, what we're saying is that the molecules are moving around faster. Let me skip ahead for a second. I'm gonna come back to this. I just want to show you a picture. I don't even have the picture. Fine. Try to imagine our water molecules, for example, right? They're moving around. When I say that things move around, like a molecule will spin, it'll vibrate, it'll stretch and compress, it'll rotate. Right? Molecules do all kinds of stuff. When I say move around, that's what I mean. I don't just mean they're bouncing around, which they are doing that. They're moving around and bouncing off of things and bouncing off each other. But they also literally spin and vibrate and shake, whatever. They do all this. And the more they move, again, the faster they move, the more they move, the hotter things get. So try to imagine this. If we were all stand up, I'm not going to do this, probably get in trouble for it. If we were all stand up and hold hands, like I'm holding her hand, and then her other hand's holding his hand, his other hand's holding his hand. If we just all did that, we were holding hands. And I said, all right, guys, just shake as wild as you can, right? We would do our best, but it wouldn't be too wild yet, right? Because we're all holding hands. It wouldn't be until we got enough wildness into it, where we broke our hands or let go of each other's hands, then we could really move around, right? If I'm holding their hands, I can't do much. As soon as I'm not holding anybody's hands, I can just do somersaults on the floor and flop around like a fish, roll around, whatever. But while I'm holding their hands, I can't do that. Does that make sense? It's the same with water molecules. So here they are, hydrogen bonded to each other. You keep putting heat into it, trying to heat them up, and they're moving around a little, but they're kind of stuck with each other, right? And it isn't until you put so much energy into it that finally those things break. And then they start getting wild, and then the temperature really rises, which is also basically boiling point of water. So yeah, just try to picture that in your brain. This is why water is so good at resisting temperature change. And again, that's useful for everyday life. If you're trying to cool things down or heat things up, water really helps. For example, if you get home, I don't know how old you guys are, you want a cold beer, you just got it from the store, and it's not cold at all, it's room temperature. It'd be quicker for you to put it in ice water than put it in the freezer. Even though the ice water is not as cold as the air in the freezer, because it's water, it's absorbing that heat more. So think about that again. It just shows you water is really good at moderating temperatures because it's really good at being very slow to change its temperature. Anyway, so like I said, the main reason behind this is because they have these hydrogen bonds, so it's hard for them to move. So they keep just absorbing energy, and it's not getting too hot because they're not wiggling around too much. And then finally it does, and then the temperature really rises. That's the boiling point. Blah, blah, blah. The opposite of that, which is this bullet point right here, is basically saying the opposite happens when it cools down, right? So again, they're moving around a lot, and they can absorb a lot of energy before they change the temperature. That's it. That's the most important thing. If you remember anything from this slide, water can change temperature. It takes a lot to change the temperature of water. Anyway, so why is that important? Well, water moderates temperatures. And because of that, on Earth, the temperatures stay within the limits that permit life. So for example, when it's really hot, it's going to store that heat from the sun, right? And then it slowly puts that off in cool periods. How many of you have ever been to a desert? Oh man. Well, you'll know. You have. Which desert was it? Do you remember?
We were out west.
Okay. Do you remember when? Like, not like year, but time of year?
It was summer.
Summer. So I don't know if it will happen for summer. It all depends where you are. But very often in a desert, it gets really hot during the day, but there's no water to absorb all that sun energy. It's just all that sun energy is there. It's just getting hot. And then at night, it gets cool, like pretty cold, because there's no energy to be then slowly released at night because there was nothing slowly absorbing it during the day. Anyway, that's why deserts are so hot, or That's why deserts have such fluctuation. That's also why usually the middle of the continent usually has higher fluctuations of temperature than the coastal areas. Like Seattle, for example, there's not that much of a change relatively to their temperature as the months go on. Because they're right next to the ocean. The ocean doesn't fluctuate much. So anyway, there's that. And then there's something called evaporative cooling. And you guys know that as sweating, right? So when you sweat, that cools you down. So again, I already talked about the desert. Another good example is, where are we at here? Here's London, right? Here's England. If you were to draw a line, that's way up in Canada. Now, when you think of Canada, what do you think of as far as the climate? You think warm, you think hot, you think cold?
I think cold.
Me too, because usually Canada or Alaska, if you keep drawing the line, that's cold stuff, right? But London, it's really not as cold. Why? Because it's right there next to the water. And I could go on and on about that, but
It's still really cold in England though.
yeah. But we were talking about like, how long have you been here?
3 weeks.
Okay, oh shoot. Well, so it gets probably about as cold. Sometimes it snows, but not always, right?
Yeah.
But it's never like,
It snows a little, or like the highest it normally gets during the summer is like 20 degrees.
see, Celsius.
Celsius.
Yeah. And again, that's because look how high north it is as far as latitude is concerned. It's also right there next to the water. So anyway, that's how that works. The last word for attendance is going to be sweat, for those of you online. When we get back, we'll talk about the biological significance of ice floating. For those of you who want to do the WVSU pictures, let's do it out in the hallway because people are waiting on us. And as usual, if I could have a volunteer to take the picture, or somebody who's not in it, that would be good too. Sure.
Is the, ladder gets in this one.
So good. Remember, if you came in late, make sure to email me to let me know you came in late.